Hey guys, so these are the notes for Monday. Um, if you didn't get a packet, well, you should have a packet, but if for some reason, come and grab one. I will check these for completion, so consider it an assignment and try not to fast forward or anything just to get it done because this is a really important topic. Some books, in a book it's called accumulated change problems, but I actually like to call these, so also known as rate in, rate out. So the general scenario is, and again, there's twists to it, but generally there's a situation usually where there's a quantity present. So let's just say it's chicken nuggets in the lunchroom. And before first lunch starts, there's a bin, and in that bin is a bunch of nuggets. If the bin's empty, then obviously we would have a 0 here for the amount at the start. But here's all these little nuggets in here. That's the starting amount. And that'll usually be given to you. It'll say like, n of 0 equals 50, which means at times 0, we have 50 nuggets in there. So then we also have a rate that nuggets are being put in. I'm going to call that R of t into the bin. So this would be, the label would be nuggets, so let's do nugs, let's say per minute. All right, then we also have the rate that you guys are taking them out when you're in the lunch line. So let's call this rate out, maybe E of t for exit. Right? And this is also in nuggets per minute. And you'll be asked a bunch of different questions about this scenario. And I can't tell you exactly what you'll be asked. I can just give you the tools for how to answer it no matter what they ask you. So when we're reading this problem, it says a quantity that is given as a rate of change, remember that's a derivative, is interpreted as a derivative with respect to time of some function. It may or may not have this prime symbol on it, so you really have to watch how they word it. They might say L of t is the rate at which people are leaving the line for the concert. So if they say that L of t is a rate, then that is a derivative. It would be like in terms of people per hour. So watch that wording if you don't see a little prime on there. If we want to find the total change over a given time period, this is the calculus of it, but let me explain to you what's going on here. This is some rate of change. Let's just throw some fake units on there. Let's suppose that that's water leaking and it's in gallons per hour. Then when I multiply it by the change in time, which would just be hours, I get what I would call net gallons at the end of that time. So that's a way to think of it with the units. Equivalently, the antiderivative of r prime is r. So really this is how much did I have at the beginning minus how much I had at the end will give me my net change, and in that case it was gallons. So a lot of times we're given either this one or this one, the amount we have at the beginning or the amount we had at the end. That's what those two mean. Those are an amount. You might say, how do you know that's an amount? Because this is a rate. Gallons per minute times minutes is gallons. Inches per hour times hours is inches. Nuggets per hour times hours is nuggets. They will give me a quantity when I integrate a rate. So a lot of times what we'll do is we'll rewrite that. You might even want to picture adding the R1 over to this side, and you would get this statement. What is this statement really saying? It's saying that the amount present at the end will equal the amount I started with. Plus what I'd call the net change or the accumulated change. I'm going to put plus the accumulation. And again, it's hard when we don't have a situation, but I just want you to get the notation of it down. So let's draw a little line here, and I'll tell you what you'll be given. You will be given some rate of change, either in or out or both rate in and rate out. So we're going to write when given a rate. And I'm going to put a little S here because sometimes, like I said, sometimes, like last year's FRQ on this topic, it told them how many people were on an escalator at the beginning. And then it told them the rate that people were stepping on to the escalator. So I could figure out how many people got on, right, by integrating that rate, because it would have been in people per minute, dt, which is in minutes, which would give me the people getting on the escalator. It then told me how many were getting off as well, and kids were asked a bunch of different questions about it. When given a rate, such as maybe the rate is labeled W prime, but that would, let's say that's the rate that water in centimeters cubed is leaking per hour. Maybe my rate was just R of t, and they didn't put a derivative on it, but they said R of t is the rate at which cars are driving through that intersection every minute. Or maybe they call it just plain E of t. Maybe that's the rate that people are exiting the theater each minute, correct? So when we're given the rates of change, it's really, really important that you understand that we integrate to get an amount of, and I'm going to put blank. It depends on the situation. The amount or volume of water that's leaked out, the amount or number of cars that went through the intersection, the people who left the theater. So each of these, if I were to integrate this, I'd get centimeters cubed. If I integrate this, I would get cars. If I integrate this, I would get people. All right, so we're going to go kind of take a look here. So we're just going to do a graphical example. I might not do all of the arithmetic just to save some time, but just so you get an idea of the situation. So we have a camp, and they're at a cookout that lasts 45 minutes. So they're giving me my time interval, which is 0 to 45 minutes, so just so you know. They're giving me two functions. It says C of t represents the rate. So this is a derivative, even though I don't see the prime on it. The word rate absorbs my word derivative or my symbol for a derivative. It's the rate that burgers are pulled off the grill. So here's what we've got. We've got this bin that's holding burgers, and they're taking them off the grill and putting them into the bin at a rate of C of t burgers per minute. All right, then the campers are coming to the cookout and they're taking them out and eating them. And that is given a different title. Let's go see what it is. I haven't done this since last year. So E of t shows the rate. So again, this is a derivative at which campers are served the hamburgers, of which all will be eaten. So they're saying, all right, everyone that is served gets eaten. So I would call that a rate out, which is also in burgers. So I'm just going to write burgs per minute. If there's nothing in the bin when I start, then I'd put a 0 in here. But it's always good to read the whole question, and this one says there are 20 burgers already in the warming tray before this meal begins. So I have 20 burgers. I have them going in at a rate of C of t and out as a rate of E of t. This problem is unique because it's a graphical interpretation, which means to integrate, we're going to have to be finding those areas under the curve. So let's just start with part A. How many are eaten? That has nothing to do with the rate that they're going in or how many are in at any given time. It is simply about the E of t functions. How many burgers? I need to integrate my rate to get my accumulated amount. So we will do this from 0 to 45 because it says throughout the cookout. Notice the labels on this. This is burgers per minute times change in time, which is in minutes, cancel, cancel, will give me the number of burgers eaten during the course of the cookout. So I go to the graph and I realize that the dashed lines represent E of t. So I don't look at anything else except I'll do it in blue. This is the rate that the kids are eating the burgers. So the camp out starts and kids start to get in line. They start to eat. They're getting in line and faster and faster and faster and faster and faster and faster and faster. They're still taking them out of the bin, but slower and slower and slower and slower and slower. And then it really tails off because it's becoming to be the end of the cookout. And at the end, I am done. But the whole time, right, we have a positive rate. So the whole time I've got burgers being eaten throughout that whole cookout. To find how many, I would just do my minutes, and this is burgers per minute. So I'm really doing an area model. I guess the easiest way to do the area of this would probably be to do this triangle, then I probably do two trapezoids. I'm not going to do that. I'm going to assume you could get the area of the triangle and the area of the two trapezoids. Remember, the area of a trapezoid is 1/2 of its height, which is the distance between the parallel bases, times the sum of the bases, which would be 9 plus 3. But I'm not going to do that. I'm going to assume you could do that. We'd get all of those and we'd put it right here. For part B, find the time intervals during which the number of hamburgers in the warming tray is decreasing. So what I need is for my rate out to be greater than my rate in. So I need my rate out, which is my E of t, the red, to be greater than my rate in. These are cooking at a constant rate right here. They're just, you've got some cook that's going on, putting them in the bin, boom, boom. They're like, we better slow down. The cookout's starting to end. People are eating them slower, correct? Where was the number of burgers in the tray decreasing? Well, from right here to right here, I am eating them at a faster rate than I am making them, which means the number in the tray will decrease. Also over here, I am eating them faster than I am making them. So we would say, and again, I call it rate out is greater than rate in. So I'd say on the interval from 10 to 20, open or closed, it doesn't matter, union 40 to 45. So again, it doesn't matter that this is hamburgers. It could be anything. If we want an amount to decrease, rate out's got to be greater than rate in. If we want an amount to increase, rate in has to exceed rate out. So for part C, it says, at what time is the number of hamburgers in the warming tray at the least? When it says questions like this would be considered an absolute minimum. So what I really need to do is to figure out, well, what's my function? I need to know how many burgers are going to be in the tray. It says in the tray. I should say in the tray. I would probably want to write a function for that. So my burgers in the tray at any given time. By the way, this is often the case where you need to write your own function. It's called your own accumulation function. You don't have to call it B of t. You can call it anything you want. But at any given time, how many burgers would there be? So back to my picture. I will have started with 20, and I'm going to make a candidate table because for absolute mins or maxes, I have to consider the endpoints. And let's talk about why. If rate in is always greater than rate out, so picture that. The amount in is always greater than the amount out. Then I'll be at a maximum at the end and a minimum at the beginning. So we have to consider the endpoint. So I'd consider at time 0, there were 20 burgers, and at time 45, I would have answered that in part A. So I'm just going to write box burgers because, well, actually, that's not even the case. I'd actually have to figure that out. All right, so let's go back to the problem. I would do 20 plus the amount that goes in the bin on that time period. So I'd 0 to t. My amount going in the bin is called C of t. And you can call it, a lot of times you'll see College Board switching the variables because they don't like to have like x going in for x. So either way, they just call it a spelling error if you don't do that. So you can call, I actually like to just do this. I think it's I'm just going to go like that. Then I do minus the rate that they're leaving. All right. Next up, a function achieves its maximum, absolute, max or min at the endpoints or anywhere where the derivative is 0 or at critical values. Now watch what happens when I take a derivative of my burger function. The constant goes to 0. The derivative of the integral is a dump and derive. It just is c of t. And then this one will be e of t. And we're looking for where that derivative equals 0. So basically, and this is what's hard for kids to wrap their brain around, is the calculus of it. So let's step back a second. Really what this means is that if we want to find where things are at a max, okay, let's even get out of the burger scenario. Let's suppose it's a swimming pool and it's got a leak in it. Let's go put that on here. It's got a little leak in it, right? But I've got the hose putting water in it. And there's already some water in the pool. If I'm always putting water in faster, so rate in is always greater than rate out, then I'll have the maximum amount of water at the end and a minimum at the beginning, because it's just going to be going up and up and up and up the whole time. Likewise, if it's leaking way faster the whole time, then I'm putting water into it. Then it was at a max at the beginning, and it's basically just going down the whole time, and it's at a min at the end. So if rate in never crosses rate out, then the max and the mins are at the endpoints. I want that to settle for you because it'll make these problems way easier. If you take away the calculus and just think about it in common sense, if there's always a rate in that's greater than a rate out, or vice versa, the maxes and the min will be at the beginning and the end. If not, then they will occur anywhere where rate in equals or crosses rate out. So really, if you want to skip this whole derivative deal, you can just say I set rate in equal to rate out. And basically what we'll be doing is finding critical values. So back to my graph, my candidates for absolute maximum would be anywhere where my rate in equals rate out. So watch what's happening. Oops, sorry. Watch what's happening on this picture. So they're cooking them faster than the campers are eating them. So at this point, the number of burgers is increasing. Rate in is exceeding rate out. So that pile is getting bigger and bigger and bigger in the bin. But then, so this is a critical value, but then rate in out starts to exceed all the way to here. So let's talk about what we were asked. We were asked for when it was at its least. Okay, so it would be at its least right here, correct? Where it was after the interval where they were taking them out faster than they were eating them. All right, so I'm going to leave that table off till we get to the next one. I'm going to skip this guy too. We're going to go to the gravel pit. So we're going to hop right in and take a very typical AP FRQ on rate in and rate out. I can't tell you what your situation will be. I can't tell you what questions they'll ask you. They'll throw weird things in, as you've seen, as we start to do more of them. But I'm fairly certain you'll have one along these lines. All right, so I told you last year theirs was an elevator problem. The year before it was bananas being stocked at a grocery store. There were some on the shelf. Here's my bananas. And then a stock boy was stocking them and people were taking them out. And they were asked questions. What questions? I don't even remember. They're different every year, but the situation is similar. So let's tackle this gravel pit problem. First thing I would do is wrap your brain around the picture. Situation, and draw a picture. On a certain workday, the rate, so they're giving me a rate, in tons per hour at which unprocessed gravel arrives, I'd call that rate in, at a gravel, I don't know what that word, processing plant is what it said, is modeled by G of T. I would go down here and I get an idea that, okay, I've got this gravel pit, here's my pile of gravel, right? The rate that gravel is arriving, so I could even draw a little truck, but is G of T, and this is in tons per hour, and it's a function that changes as time goes by. Make sure we're in radian mode, right? And then it says, during the hours of operation, so for the 8-hour workday, that plant is working, it's processing this gravel and shipping it out at a constant rate of 100. So this is constant, 100 tons per hour. So understand that it's coming in at this rate, it's leaving at this rate. So after 2 hours, if I wanted to know the rate, how much, let's go to the questions because I think they're going to ask you that. So do we have anything in the pile at the beginning? Let's see. Yep, 500 tons at time 0. So there's already 500 here. So that's the situation. Wrap your brain around it. And let's go. Letter A. Find G prime of 5. That would be the derivative of G. And this is calculator active. So you just use your Math 8 button on G. Make sure you identify it and label it, but you don't have to write the derivative with respect to dt of G of T at T equals 5. You don't need to write that. You can simply write this. But we would do that on our calculator with our Math 8 button. A lot of times I like to load G of T into Y1 and use my vars. I'm going to let you do that. And that's something I'll check with the notes that you've actually gone through and finished this up. If I load the calculator, it slows down my smartboard. Now let's talk about the label. Since this G of T is in tons per hour and I just did its derivative, my label would be tons per hour squared. So there's my label. It says interpret your answer in the context of this problem. Well, I'm actually going to go to my calculator to see if that's positive. Oh, I don't even have a calculator. So I don't know what that number is. So we'll talk about that when you come into class, how you word your answer. We'll wait to see what the number is. But it's actually the rate at which the rate is changing. It says find the total amount of unprocessed gravel that arrives to the plant during the 8-hour workday. That is only about G of T. So all I need to do is integrate my arrives at the plant rate from 0 to 8. Again, tons per hour times change in hours yields accumulation of tons that fell onto that pile during the 8-hour workday. And you would have to type that into your calculator and make sure you label it, and that's an easy question. Letter C. Is the amount of unprocessed gravel at the plant, that would be this pile right here, is it increasing or decreasing at 5 hours? Well, basically, for the increasing, decreasing questions, I just compare rate in at 5 to rate out at 5. Well, I found rate in at 5 in part A, but I don't have my calculator. So I'm just going to say G prime of 5 equals, and you'll write that number down because you will have done it. Rate out at 5 hours. Okay, so it would be 100 per hour times 5 hours, which would be 500 tons. Oh, sorry, I lied. The rate out, that's how many tons there would be. The rate out is a constant. 100 tons per hour. So what I'll do is I'll compare this number. If it is bigger, I would say that the pile is increasing. If it's less than 100, I'd say that the pile is decreasing. If rate in is greater than rate out, this pile is going to grow. If rate out is greater than rate in, it will shrink. If they are equal, the pile will remain the same height. Letter D is the question that always gets kids. It's still getting kids in BC, although most of them are done making mistakes on it. By the way, this is always a BC crossover, so next year you'll be doing this one too, juniors. So it says, what is the maximum amount of unprocessed gravel? All right, so an absolute maximum occurs either at an endpoint or at any critical values. I need a function for the amount of unprocessed gravel. I'm going to call it T. How much is there at any given time? So really what that would be is the 500 that was there at the beginning, plus the amount that gets dumped on the pile, which would be to integrate my rate in, minus the amount that gets removed. Done. This guy's easy to see. It's just 100 T. It makes sense. After 2 hours at 100 tons per hour, 200 tons would be taken off the pile. But you can just leave it like that. So at 0, it was a 500. At 8, I would go plug an 8 in for T. So I'd go up at 8 and I'd do a 500 plus from 0 to 8 of G of T. It's calculator active minus, and then if you want to just call this 100T, it'd just be minus 100 times 8. Word for the wise here too. If this had been an open, just hold off on that. There's some stuff I just need to discuss with you outside of these video notes just to make sure everybody, I know some of you guys speeded ahead and fast forward me, and there's a few important things I don't want you skipping over. So that's my function for A of T right here. This would be at the start, this would be at the end. Again, if rate in is always greater than rate out, my min's at the beginning, my max is at the end. If rate out is always greater than rate in, then my max is at the beginning and my min's at the end. The only time that I can have a max or a min is if rate in at some point crosses, sorry, this is G of T, crosses rate out. So equivalently on my calculator, it's where G of T minus 100 equals 0. You can jump right to that. Or you could say it's when the derivative equals 0. Watch what you get when you take the derivative of these. Right? So the derivative of this would be 0. The derivative of this would be dump and derive G of T. The antiderivative of 100 is 100T. Its derivative is 100. So this would fall out with the calculus, but I really just want you to think rate in has to equal rate out. If that never happens, the maxes and the mins are at the endpoints. So what you do is you go to your calculator and you go to Y1 and you actually enter the G of T function minus 100. Set your window to go from 0 to 8 by ones. Okay, so I would go set your window. Again, for the y's, I'm just looking for where it crosses the y-axis, so maybe just have it go from -2 to 2. That's why we get it equal from 0 to 0. You'll get some critical points. So at t equals blank, there's probably usually 2 of them. We write them down. I don't know what they are. I want you doing that. That's what I'm going to check. So you might want to pause me, make sure you get a calculator. If you're not sure if you're doing it right, you can always Google 2013 AP Calculus AB. Go find the key. It's not a secure doc at all. It was the actual 2013. So once you get these critical values, I'm going to just call them A and B because I'm not using my calculator. It actually works out well. It'll help me know if you took the notes authentically. What I do is I plug that number into my amount function. So how much would I have at this first critical value? 500 plus I'll integrate from 0 to A dt minus 100a, or you can integrate from 0 to, it doesn't matter. One of these is probably going to be when we were at a max or a min. It's almost always a critical value, and it'll say student identifies interior candidate, that kind of thing. So what is the maximum amount of gravel? So we have to read the question when it says what is the maximum amount. Let's suppose it ends up being this one. Okay, we would say the max is blank at t equals, and then it'd be that b. And I would like you to fill that in for me. All right, so we'll be doing some more of this. You might even want to keep working in either, well, I know we have the related rate packet out there, so for Monday night, you could either tackle a couple of these FRQs or you could tackle your related rate problem packet. Remember, for the related rates, you pick 10 multiple choice. Pick the 10 that aren't your favorites. I'd like you to pick the 10 multiple choice that make you go, ugh, don't pick these. Yay, I know how to do the ladder problem. Don't choose that then. And then do 2 FRQs. Also the 2 that make you go like this, not the 2 that make you smile. The key is posted, and you guys have a good one.